When inspecting motor windings, there are several key aspects to consider, encompassing both physical and electrical assessments. The physical inspection involves a detailed examination of the winding's condition, looking for signs of damage or degradation. Firstly, check for charring, discoloration, or burn marks on the windings. These are visual indicators of overheating, which can severely compromise the insulation and overall performance of the motor. Overheating can be caused by excessive current, inadequate ventilation, or prolonged operation beyond the motor's rated capacity. Secondly, examine the windings for any deformation. Broken wires, loose coils, or distortions can significantly affect the motor's performance, leading to reduced efficiency, increased vibration, and potential failure. These issues may arise from mechanical stress, vibration, or thermal cycling. Thirdly, carefully inspect the insulation for cuts or cracks. These faults can create pathways for electrical shorts or ground faults, posing a safety hazard and potentially damaging the motor and connected equipment. Insulation damage can result from physical abrasion, chemical exposure, or thermal aging. Fourthly, look for dirt, moisture, or corrosion on the windings. These contaminants can interfere with the insulation's integrity and hinder heat dissipation, exacerbating the risk of overheating and insulation breakdown. Moisture can lead to corrosion, while dirt can act as an insulator, trapping heat within the windings. Fifthly, check the overhangs to ensure proper clearance from the stator slots and end plates. Insufficient clearance can lead to arcing and insulation failure, particularly during motor startup or under heavy load conditions. Overhangs are the portions of the windings that extend beyond the stator slots. The electrical inspection complements the physical assessment by providing quantitative data on the winding's electrical characteristics. Firstly, perform resistance measurements to check for continuity, high resistance due to breaks, or low resistance indicating shorts. Use a multimeter to measure the resistance between different points in the winding, comparing the readings to the manufacturer's specifications. High resistance suggests a broken or partially broken wire, while low resistance indicates a short circuit between windings or to ground. Secondly, conduct an insulation resistance test, also known as an insulation resistance test. This test measures the resistance between the windings and ground, providing an indication of the insulation's integrity. Use an insulation resistance tester, often called a megometer, to apply a test voltage, typically 500 volts or 1000 volts direct current, and measure the resultant current flow. The higher the resistance, the better the insulation. A common rule of thumb is that the insulation resistance should be at least 1 megaohms plus 1 megaohms per 1000 volts of operating voltage. Thirdly, perform a high-pot test, which applies a high voltage to the windings to detect insulation breakdowns. This test is typically performed after an insulation resistance test and can reveal weaknesses in the insulation that may not be apparent under normal operating conditions. Use a high-potential tester to gradually increase the voltage, monitoring the current flow for any signs of breakdown. This test should be performed with caution, as it can further damage weakened insulation. Fourthly, consider performing a surge test, which simulates electrical transients to identify weak insulation. This test is particularly useful for detecting insulation weaknesses caused by voltage surges or spikes. A surge tester applies a high voltage pulse to the windings, and the resulting waveform is analyzed to identify any reflections or distortions that indicate insulation problems. In addition to these physical and electrical inspections, there are other considerations to keep in mind. Firstly, identify the winding type, ensuring it is compatible with the motor design. Motors can use different types of windings, such as random wound or foam wound, each with its own characteristics and performance capabilities. Random wound windings are typically used in smaller motors, while foam wound windings are more common in larger motors. Secondly, check the coil pitch to ensure proper alignment and uniformity. The coil pitch refers to the distance between the two sides of a coil within the winding. A consistent coil pitch can lead to uneven magnetic fields and reduce motor performance. Thirdly, verify that the windings are adequately filled in the stator slots. Insufficient slot fill can result in reduced heat dissipation and increased risk of overheating. The windings should be tightly packed within the slots to maximize heat transfer to the stator core. Fourthly, inspect the lead connections for secure connections and strain relief. Loose or corroded connections can cause voltage drops and overheating, while inadequate strain relief can lead to broken wires. The lead connection should be properly crimped or soldered and protected from mechanical stress. Fifthly, check for insulation that meets surge voltage requirements. The insulation should be able to withstand the expected surge voltages in the operating environment. Surge voltages can be caused by lightning strikes, switching operations, or other electrical disturbances. Sixthly, verify that the insulation is suitable for the operating environment, particularly with respect to moisture resistance. Motors operating in humid or wet environments require insulation that is resistant to moisture absorption. Finally, assess the condition of the windings based on operating temperature and duration. Thermal aging can gradually degrade the insulation, reducing its ability to withstand electrical stress. The higher the operating temperature and the longer the duration of operation, the faster the insulation will age. Regular inspections and testing can help identify potential problems before they lead to motor failure. When performing insulation resistance tests, it is essential to interpret the results correctly. A high insulation resistance value indicates good insulation, while a low value suggests insulation degradation or contamination. However, the interpretation of insulation resistance values can be influenced by several factors, including temperature, humidity, and the presence of surface leakage currents. To ensure accurate results, it is recommended to perform insulation resistance tests under controlled conditions and to compare the results to previous readings or manufacturer's specifications. Temperature can significantly affect insulation resistance, with higher temperatures generally resulting in lower resistance values. Therefore, it is important to correct the insulation resistance readings for temperature variations. Humidity can also affect insulation resistance, particularly if the insulation is contaminated with moisture-absorbing materials. Surface leakage currents can also reduce the apparent insulation resistance. These currents flow along the surface of the insulation due to contamination or moisture. To minimize the effects of surface leakage currents, it is recommended to clean the insulation surface before performing the test. High-pot testing is a valuable tool for detecting insulation weaknesses, but it should be performed with caution to avoid further damaging the insulation. The test voltage should be applied gradually, and the current flow should be closely monitored. If the current exceeds a predetermined threshold, the test should be stopped immediately to prevent insulation breakdown. It is also important to ensure that the equipment being tested is properly grounded to prevent electrical shock hazards. Surge testing is a more advanced technique for detecting insulation weaknesses that may not be apparent with other tests. This test is particularly useful for identifying insulation damage caused by voltage surges or spikes. The surge tester applies a high voltage pulse to the windings, and the resulting waveform is analyzed to identify any reflections or distortions that indicate insulation problems. The interpretation of surge test results requires specialized knowledge and experience. The waveform analysis can reveal various types of insulation defects, such as shorted turns, ground faults, and insulation voids. In addition to these electrical tests, visual inspection is also crucial for identifying potential problems. Look for signs of overheating, such as discoloration, blistering, or charring of the insulation. Also, check for any physical damage to the windings, such as cracks, cuts, or abrasions. Pay close attention to the lead connections, ensuring that they are tight and free from corrosion. Also, it is important to check the motor's operating environment. Excessive moisture, dirt, or chemicals can accelerate insulation degradation. If the motor is operating in a harsh environment, it may be necessary to take additional precautions to protect the windings. This may include using special insulation materials, providing additional ventilation, or installing protective enclosures. Regular motor maintenance is essential for ensuring reliable operation and extending the motor's lifespan. This includes periodic cleaning, lubrication, and inspection of the windings. By identifying and addressing potential problems early on, you can prevent costly repairs and downtime. When performing any type of electrical testing, it is important to follow all safety precautions. Always to energize the equipment before working on it, and use appropriate personal protective equipment such as gloves and safety glasses. Also, be sure to use properly calibrated test equipment and to follow the manufacturer's instructions. The NEC National Electrical Code provides guidelines for motor protection and wiring. Article 430 covers motors, motor circuits, and controllers. It includes requirements for overcurrent protection, overload protection, and grounding. Proper application of these guidelines is essential for ensuring the safe and reliable operation of motors. For example, NEC Table 430.52 provides the maximum rating or setting for motor branch circuit, short circuit, and ground fault protective devices. This table specifies the maximum allowable size of the circuit breaker or fuses based on the motor's full load current and the type of motor. NEC Section 430.122 covers motor control circuits. This section includes requirements for control circuit conductors, overcurrent protection, and disconnecting means. Proper design and installation of motor control circuits are essential for ensuring the safe and reliable operation of the motor control system. When selecting a motor for a particular application, it is important to consider the motor's voltage rating. Common motor voltage ratings include 120 volts, 208 volts, 240 volts, 480 volts, and 600 volts. The motor's voltage rating must be compatible with the available power supply. Also, it is important to consider the motor's horsepower rating. The horsepower rating indicates the motor's mechanical power output. The motor's horsepower rating must be sufficient to drive the load. When installing a motor, it is important to ensure that it is properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock hazards. The grounding conductor must be sized according to NEC Table 250.122, which specifies the minimum size of equipment grounding conductors for various circuit ratings. Also, it is important to protect motor circuits from overloads. Overloads can occur when the motor is subjected to excessive load, which can cause it to overheat and fail. Overload protection can be provided by fuses, circuit breakers, or overload relays. The overload protection device must be sized according to NEC Section 430.32, which specifies the maximum allowable rating or setting of the overload protection device based on the motor's full load current. In addition to overload protection, it is also important to protect motor circuits from short circuits and ground faults. Short circuits and ground faults can cause large currents to flow, which can damage the motor and the electrical system. Short circuit and ground fault protection can be provided by fuses or circuit breakers. This short circuit and ground fault protection device must be sized according to NEC Section 430.52. When working on motors, it is important to be aware of the potential hazards. Motors can contain high voltages and currents, which can be lethal. Always to energize the motor before working on it and use appropriate personal protective equipment. Also, be sure to follow all safety precautions and to consult with a qualified electrician if you are unsure about any aspect of the work. Remember to consult the manufacturer's specifications and applicable electrical codes for detailed information on motor installation, operation, and maintenance. Regular inspection and testing of motor windings are crucial for maintaining their reliability and preventing unexpected failures. By following these guidelines, you can ensure the safe and efficient operation of your motors for many years to come. Furthermore, the operating environment plays a significant role in the longevity of motor windings. High ambient temperatures, excessive humidity, and the presence of corrosive substances can accelerate the degradation of insulation materials. In such environments, it may be necessary to employ special motor enclosures, insulation coatings, or cooling systems to protect the windings from premature failure. Consider the use of totally enclosed fan-cooled, or TEFC motors in dusty or dirty environments, as these designs prevent contaminants from entering the motor and damaging the windings. Additionally, ensure proper ventilation around the motor to dissipate heat effectively. Inadequate ventilation can lead to elevated winding temperatures, which can significantly shorten the insulation lifespan. Regularly cleaning the motor housing and ventilation openings can help maintain adequate airflow. Proper lubrication of motor bearings is also essential for preventing winding failures. Worn or improperly lubricated bearings can cause excessive vibration and heat, which can be transmitted to the windings, leading to insulation damage. Follow the manufacturer's recommendations for bearing lubrication frequency and type. Employ vibration monitoring techniques to detect bearing problems early on. Increased vibration levels can indicate bearing wear or imbalance, allowing for timely maintenance and preventing further damage to the motor and windings. When replacing motor windings, it is crucial to select the correct type and size of wire. Using undersized wire can lead to overheating and premature failure, while using the wrong type of insulation can compromise the motor's performance and safety. Consult the motor's nameplate and manufacturer's specifications to determine the appropriate wire gauge and insulation class. Ensure that the replacement windings are properly installed and secured to prevent movement or vibration. Loose windings can rub against the stator core, causing insulation damage and eventual failure. After rewinding a motor, it is essential to perform thorough testing to verify the integrity of the new windings. This includes insulation resistance tests, high-pot tests, and surge tests, as previously discussed. Compare the test results to the manufacturer's specifications to ensure that the windings meet the required performance standards. Document all inspection and testing procedures, including the date, time, and results. This documentation can be valuable for tracking motor performance over time and identifying potential problems early on. Maintain a comprehensive motor maintenance log that includes information on all inspections, tests, repairs, and replacements. This log can serve as a valuable resource for planning future maintenance activities and preventing unexpected failures. Consider implementing a predictive maintenance program that uses condition monitoring techniques to assess the health of motor windings. This may involve using infrared thermography to detect hotspots, vibration analysis to identify mechanical problems, and oil analysis to assess bearing condition. By proactively monitoring motor condition, you can identify potential problems before they lead to failures, reducing downtime and maintenance costs. In summary, inspecting motor windings involves a combination of physical examination, electrical testing, and careful consideration of the operating environment. By following these guidelines, you can ensure the reliable and efficient operation of your motors, extending their lifespan and minimizing the risk of unexpected failures. Remember to prioritize safety when working with electrical equipment and consult with qualified professionals when necessary.